Throughout this video cast, we'll take a look at some conversions between units for pressure. We'll also take a look at some of the basic laws that govern how gases act according to their four main characteristics: pressure, volume, temperature, and number of moles of gas. And we'll look at some stoichiometry, something called the combined gas laws that come together and allow us to make some calculations when we assume gases are in an ideal condition. We'll start here with sample exercise 10.1, where we're converting 0.357 atmospheres to torr. Rewrite your 0.357 atmospheres, put a multiply sign, put a line, take the atmospheres and put it in a position where it's going to cancel, and put torr as your new set of units. The relationship between atmosphere and torr, which you saw in the last video cast, is that 1 atmosphere is equal to 760 torr. So we take the 760 and put it on top with the torr, 1 atmosphere down here below. Notice the two units cancel with one another. Multiply those together and you get a total of 271 torr. Second example is torr to atmosphere, which is just the opposite of what we did. Take the 6.6 times 10 to the negative 2 torr. Put torr in a position where it's going to cancel this time and put atmospheres as your new set of units. In 1 atmosphere, there's 760 torr. And doing the division on your calculator, you should end up with 8.7 times 10 to the negative 5th ATMs. Lastly, kilopascals to torr. The relationship between kilopascals and torr is there's 101.3 kilopascals in 760 torr. Notice something isn't 1 for a change in a conversion factor. Write down your 147.2 kPa, put a multiply sign, put a line, put kPa in a position where it's going to cancel. Torr is your new set of units. 760 on the top, 101.3 on the bottom. Do your multiplication and division, and you should end up with 1104 torr. Some simple conversions, but you should become fast at them. You should become so used to them that you know these relationships between atmosphere and torr and millimeters of mercury and kilopascals. And remember that torr and millimeters of mercury are the same thing. Let's look at the next sample exercise, 10.3. In this one, we're going to take a look at a confined cylinder, like is in figure 10.2 in your textbook, 10.12, I'm sorry. It looks something like this in your book, and I'll draw a figure that's very similar. Notice there's a small valve at the bottom, and this is a moving piston that can squish this sample of gas that's inside of it. So we'll draw something similar to it right here. Here's the piston. And here is our confined gas. And then down here we have a little valve as well that we could let gas in or put gas out. Now there are three main, actually four, but we'll look at three main relationships between temperature, pressure, and volume and number of moles of gas. The first one is the relationship between temperature and pressure. As long as volume and number of moles of gas are constant, if temperature goes down, pressure goes down. If you think about it, temperature, as you decrease it, the molecules get slower, they collide less, and therefore there's less collisions of the molecules with themselves and the container, and therefore there's less pressure. Some people call this the toilet paper relationship, TP. T goes down, P goes down. The second relationship is between temperature and volume. Temperature and volume are related in that as temperature goes up, volume also goes up, as long as pressure and number of moles of gas are held constant. This can be illustrated by the old-time television where one antenna goes up, the other antenna goes up, or one foot goes down, the other foot goes down. It's a direct relationship, just like the TP relationship. The last relationship is pressure and volume. Sometimes it's written like this, VP, because it's like the vice president. And this one is an indirect, or shall we say, an inverse relationship, because if pressure goes down, volume can go up. Pressure goes down, volume goes up. Think of it as when the president goes down, the vice president goes up. Pressure goes down, there's less collisions of the molecule, they can spread out further, and as long as temperature and number of moles of gas are constant, it can spread out and occupy a larger volume. Knowing those three relationships, we should be able to answer the questions in sample exercise 10.13. We have this gas confined in a piston cylinder, and if we heat the gas from 298 to 360 Kelvin while maintaining the piston, in other words, holding this constant right where it's at, what will happen? Well, if we heat it, we'll add energy to these gas molecules and we'll speed them up. We maintain the volume, so if temperature goes up, what happens to the pressure? The pressure will go up. So temperature goes up, pressure goes up. Pressure inside the container should increase. Second question, if we move the piston to reduce the volume from 1 liter to half a liter, now we take this piston and we squish the gas. We push it down so it's compacted. Well, what happens to it in terms of temperature, pressure, and volume? Well, obviously volume got smaller. Okay, we said we did that because we squished the piston down. If you squish the molecules closer together, they'll collide easier with each other. And so you have to say that the pressure will increase. And what about the temperature? Well, we'll assume that we held the temperature constant because it doesn't say we did anything to the temperature. But in theory, you may heat the gas up as well at the same time. Lastly, letter C, eject gas through the gas valve inlet. In other words, we're going to let some gas out down here. We'll let some gas out. Okay, if we do that, how will it affect the distance between the molecules, the pressure of the gas, and the number of moles of gas present inside of this cylinder? Well, first of all, we should have squished once we let some gas out of here, we should have made more space, and therefore we should have reduced the pressure, right? The pressure should have gone down because we let some of the gas out. We've got less moles of gas in there. And the number of moles of gas present in the cylinder, of course, would be less because we let some of the gas out of the container. These conceptual ways of taking a look at temperature, pressure, volume, and number of moles of gas can be really handy. Next sample problems we're going to take a look at from sample exercise 10.4. This question says, when calcium carbonate decomposes upon heating to give calcium oxide and carbon dioxide, a sample of calcium carbonate is decomposed and the carbon dioxide is collected in a 250 milliliter flask. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees Celsius. How many moles of CO2 gas were generated? Well, we know a lot of data. And what I recommend doing in these gas law problems is first making a table of volume, temperature, pressure, and number of moles of gas, the 4 factors that affect how a gas is actually described. And writing in what you know from the problem. Here we're told we have a 250 milliliter flask, so that's our volume. We're told that the gas has a pressure of 1.3 atms, or 1.3 atmospheres, and the temperature happens to be 31 degrees Celsius. The number of moles of gas we don't know. Well, there's a relationship between pressure, volume, temperature, and number of moles of gas that's given to us by a really simple equation. The equation is called the ideal gas law, and the ideal gas law is written as PV is equal to nRT, where P stands for pressure, and it can be in any units, just so as long as it matches up with our value that we have over here for R. We'll talk about that in a second. V stands for volume. The volume generally has to be in liters. That's the safest. N stands for number of moles of gas. R is what's called the universal gas constant. And the gas constant has several different values depending on what the pressure is. So relate the pressure to the gas constant, and then you can win a prize. And T is the Kelvin absolute temperature. Gases are always described on the Kelvin temperature scale because we want to look at them from an absolute viewpoint, looking at it from 0 Kelvin on up. Well, the universal gas constant, I'll put that over to the side here, and I'll list the 3 values that you should be fairly familiar with. R, remember, stands for the universal gas constant. It has several values. One of them is 0.0821. and this is in terms of atmospheres of pressure. The other units on that are liters per mole times Kelvin. Another way to write the universal gas constant in terms of kilopascals is 8.31 kilopascals times liters per mole times Kelvin. And lastly, the other way to write it is in terms of torr or millimeters of mercury, and this is 62.4 torr or millimeters of mercury times liters per mole Kelvin. Now your textbook generally uses this one, and if you look on the AP exam sheet that you get, I believe you get this one as a value. They put this one on here too, but they give it a little bit different units that we'll talk about later when we get into a little more detailed discussion about using the ideal gas equation. For this one, it gives us the pressure in atmospheres, so we'll use this universal gas constant right up here. Solving this equation for number of moles, because that's what they want to know, it can turn out to be N is equal to PV divided by RT. The pressure is 1.3 atmospheres. The volume is 250 milliliters, but be careful, it's got to be in liters, so 0.25 liters divided by R, which in this case is 0.0821 liters times atmospheres per mole times Kelvin. And our temperature is 31 Celsius, which when you add 273 to it, because you want to convert it to Kelvin, is 304 Kelvin. Multiply the top, divide by the things on the bottom, and I believe you end up with, I'm running out of space here, 0.013 moles of CO2 that has been produced. Our next problem, sample exercise 10.5, says the gas pressure in an aerosol can is 1 atmosphere at 25 degrees Celsius. Assuming that the gas inside obeys the ideal gas equation, what would be the pressure if the can were heated to 450 degrees Celsius? Now this is a similar problem, but we have a change in conditions. And look for when there's a change in conditions. Make yourself a table, pressure, volume, and they tell us that temperature changes as well. So initially, the pressure of the can is at 1.5 atmospheres. We're also told that the gas is inside of a can, and we're assuming that the can does not explode or expand, so we can say that the volume stays the same, and that the initial temperature is 25 degrees Celsius. Notice it's in Celsius. Now these are our initial values, so I'm going to write initial at the top right here, and I'm going to put final over here because we're going to change it to a different style of conditions. We're going to change it to 450 degrees Celsius. The temperature stays the same. And they want to know what is the final pressure. Now there's a couple of ways to do this. We can look at the pressure-temperature relationship, and you can use a simple equation that says pressure and temperature are directly related to one another. And you can use the equation P1 divided by T1 is equal to P2 divided by T2. But instead of using that equation, what I recommend is that you think through it. And you ask yourself the question, what's happening to the temperature? If the temperature goes up, what happens to the pressure? Well, the pressure also must go up as long as volume and number of moles of gas are constant. So you can take your initial pressure, 1.5 atmospheres, put a multiply sign and put a line. Converting these to Kelvin temperatures gives you 298 K and 723 Kelvin. Make a ratio between these two temperatures that will allow you to make the pressure get larger. Allow you to let the pressure get larger. Now your choices are 298 over 723 or 723 over 298. Which one would you want to choose to make the pressure get larger? Well, I'd choose the one with the bigger number on the top, right? 723 over 298. Notice your Kelvin and Kelvin cancel, and your answer will be in atmospheres, and you end up with 3.6 atmospheres. You can do the same thing just by plugging and chugging in this equation, but this way allows you to think through it right away and say, did my pressure get larger? It was supposed to get larger. Yes, I multiplied by a ratio to make it get larger. Let's look at the next sample problem. An inflated balloon has a volume of 6 liters at sea level and is allowed to ascend to an altitude until the pressure is 0.45 atmospheres. Once again, we started at sea level at 1 atmosphere, and notice it changed. So here's another time where we'll have a pressure, volume, and temperature with some initial conditions and some final conditions, and we can organize our data this way. During the ascent, the temperature of the gas falls from 22 to negative 21. Calculate the volume of the balloon at its final altitude. They even use the word final, so you know it's an initial final conditions type of problem. Well, initially we're told that the pressure is 1 atmosphere at sea level, and at the final conditions, when it rises up into the air, it ends up at 0.45 atmospheres. The volume to start with is at 6 liters. And we don't know the volume at the end. That's the thing that's a question mark. And lastly, the temperature at the beginning was 22 degrees Celsius, and at the end it was negative 21 degrees Celsius. It got quite a bit cooler. You're converting these to Kelvin right away. Don't be tempted to use the Celsius temperatures. This is 252 Kelvin, and converting this right away, this is 295 Kelvin to start with. Now, you can use the gas relationship equation, pressure initial, volume initial, divided by temperature initial is equal to pressure final, volume final times temperature final. Divided by temperature final. This equation will allow you to plug and chug the values in, and you can solve for the one that you don't know. And it works just fine. And you're given this equation even on the AP Chemistry equation sheets that you can use on the test. I recommend, though, that you take a look at this and think through it, and then you'll know for sure you got the correct answer. Start with the value that you have, 6 liters. Put a multiply sign, put a line. Now take a look at one of the changes. Take each of the changes separate. Let's just look at pressure to start with. It goes from 1 atmosphere to 0.45 atmospheres. Pressure goes down. When pressure goes down, what has to happen to volume? Well, remember the volume-pressure relationship? When one goes down, the other one goes up. They're an inversely related proportion. Well, since pressure is going down, volume is going to have to get bigger. So multiply by a relationship to make it get bigger. Well, I'll put 1 ATM over 0.45 atmospheres. That makes it get larger. Okay? Now take a look at your temperatures from 295 to 252. Temperature is going down. When temperature goes down, what happens to volume? Well, remember the TV relationship? When temperature goes up, volume goes up. When temperature goes down, volume goes down. It's a direct relationship. So we must multiply by a ratio to make it get smaller. Since the temperature is going down, the pressure's also got to go down. And the volume also has to go down. So to make it get smaller, I'll take the smaller number and put it on top. Put the larger number and put it on the bottom. And if I plugged it into this equation, I'd end up with the same exact mathematics, just like I have right here, except I thought through it when I did it here, and I know I'm going to end up with the right answer. When you multiply these together, you get about 11 liters. It turns out that the volume increased because temperature went down, and of course pressure went down as well.